Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Tatiana Rodríguez with us today.
Hello, everyone. Hi.
How are you?
Pretty okay. It's a nice morning here. Finally, spring weather.
Where is here? What's your geolocation?
Well, I am in Socorro, New Mexico.
Oh, very
and
cool.
It's been quite cold this past few weeks, but it's now nice and warmer.
Did you get a little snow and rain last week? Because we got some snows coming
We got rain and lots of wind. But
yeah. The spring ones were definitely going here in Phoenix.
Yeah.
But yeah, amazingly enough, even in Phoenix, we have some mountains that go to about 4,000 feet or so right outside, and they were snow capped. So there was actually a little bit of snow in Phoenix.
Nice view.
So Socorro being quite a bit higher on those high desert mesas, that would be great. So what's your position there in Socorro?
Yes, I am a PhD candidate at the New Mexico Institute of Mining and Technology, or New Mexico Tech, we call it. And I'll be graduating next spring, hopefully.
Oh, congratulations. I look forward to calling you Dr. Rodríguez.
Me too.
That would be very awesome.
Yes.
Very cool. And Tatiana, what do you like to do for research?
Well, I study high mass star formation using multi-scale observations of ionized and molecular flows and how they interact with the surrounding medium.
Cool. Like that awesome background image you have.
Yes, it's M43.
Very nice. Very nice. Very cool. And that is going to bring us to this very awesome APJ supplement article. It's open access, people. Go get a copy for free. Go grab it. Searching for molecular jets from high mass protostars. And Tatiana, take us away.
Yes, hi, thank you. I want to say first, thank you to all my co-authors. So Peter Hoffner, here's my advisor at New Mexico Tech. Isaac Edelman with an undergrad that we were working with, who helped me a lot with the figures in this article.
Nice.
And yeah, Esteban Araja, he's part of our NSF project fund journey. I will give a shout out to that later. And also Viviana Rotero, who is my advisor's former advisee, and she's super nice. So we are this big New Mexican family here.
Very nice.
Okay, so let's jump right into it. So as I mentioned earlier, I study high mass star formation, that is the formation of stars with more mass than 8 times the mass of our sun. Now, mainly due to their scarcity, because they're less abundant than objects like our sun, for example, and their rapid evolutionary timescales, there is still a lot that we don't know about how they are formed. One particular model that I use in my research is called the core accretion model, or turbulent core accretion model. And it's basically a scale-up version of the process lower mass objects undergo.
Okay.
In this model, the emerging protostar is accreting material from its surrounding while it's ejecting ionized material through its pole in the form of ionized jet. Now, the massive young star object usually reaches the conditions necessary for nuclear burning while still deeply embedded. So it makes it really challenging from an observational point of view to study this AU scale ionized jets, which are ejected from very close to the protostellar surface.
Okay.
As a result, there are only a handful of jets known that are driven by high mass young stellar objects. And this number has recently begun to increase with the new generation of telescopes, particularly the expansion of the VLA with the Very Large Array, which happened in 2011, more or less.
Okay.
So this expansion brought an increase in sensitivity of the instrument and allowed for several radio continuum surveys to be carried out and increase the number of jets known from high mass protostars. But this number is still small, and we're trying to increase it in order to help us better understand the nature of ionized jets.
Okay.
Now, one survey in particular that contributed a lot to how we understand jets from high mass protostars is that of Viviana Rosero et al., 2016 and 2019. As I mentioned before, Viviana is one of my co-authors, and she actually carried out this survey work as part of her dissertation, which is awesome. So what they did was observe with high sensitivity and high resolution 58 high mass star forming regions with a very large array at 1.3 and 6 centimeters.
Okay.
Now, their sample was carefully curated from infrared catalogs to target the earliest stages of high mass star formation. So that is prior to the formation of H2 regions. Okay.
All right.
So they had both cold molecular cores and hot molecular cores in their targeted sample.
Okay.
So from those 58 star forming regions, they ended up detecting 70 sources of radio continuum emission.
Okay.
Of these, several were shown to be ionized jets, but about 30 of them were classified as jet candidates. Now, what does this mean? So these jet candidates are unresolved with their silver second resolution, but they show a rising spectral index. Now, a rising spectral index at centimeter wavelength is expected from both thermal emission from a partially optically thick ionized jet, but it could also be explained by a spherical ionized region of constant density, so a very early stage H2 region. And they show also in their figure 2 how well both this model can represent the observations that they have. So we need to confirm the nature of the radio continuum associated to the jet candidates from the survey. And that's the goal of my work today.
Lovely. That's awesome. Okay.
So there are basically two ways to distinguish whether these are jets or ionized regions. One of them would be to go to higher resolution observations and see if these objects that are unresolved in the Rosero data show an elongated morphology, which is typically of ionized jets.
Yeah. Okay.
Alternatively, we can study the molecular emission associated with the jet candidate, which is actually the path that we took and led us to this work.
Okay.
So in the earliest stages of formation, if we detect a molecular flow, a molecular jet, we expect it to be directly related to an ionized jet. Okay, so basically we're trying to find molecular jets that are associated to the jet candidate to confirm that the nature of the radio continuum is indeed a jet.
Got it. I'm with you.
Cool. So to do this, we decided to use the SIO molecule. And this is because the SIO abundance is highly enriched in shock gas regions, which makes it ideal for our science goal. And we use the VLA at 7 millimeter, which is the Q band, and allowed us to observe the SIO10 rotational transitions at 43.4 gigahertz.
Cool. Okay.
Given our spectral setup, we were also able to observe the 7 millimeter continuum emission and the CS10 emission at 48.9 gigahertz.
Cool. Okay.
So in table 1, what we show here is our target region. Now we chose 10 jet candidates from the Rosero survey located in this region that I listed here. And we columns 2 and 3 show their position, their distances, luminosities, and type, which can be hot molecular core, cold molecular core, or cold molecular core with infrared emission associated with it, as is discussed in the Rosero papers.
Right.
Yeah, a little bit of water.
All good.
Okay, so the last 3 columns of table 1 show a little spoiler in which of these regions we detected 7 millimeter continuum, in which we detected SIO10 emission, and in which we detected CS10 emission. So this is a little spoiler, but I'm going to talk about it a little bit more in the results section of it.
Yeah.
Before we do jump to the results, I do want to mention that throughout the paper, I'm going to show images of only one region that will serve as an example.
Okay.
And there are analogous images for everything that I'm going to show. for all the other regions that we observed in the appendix. Okay, so keep an eye on that.
Yeah, so this is a supplement paper. There are 8 pages in the main body, and there was a whopping appendix, monster lovely appendix, with all the details of the individual system. So in fact, let's just slide down. Let's just show people the appendix.
Let's go
So
straight to the results.
do check out the appendix. It's exquisite, lovely detail on each of the various source regions. So do check it out. So let's go back up to where we were, table 2.
Yes, page 3. All right.
Yep.
So
okay.
Jump into the results. I'm going to go through each of the different things that we detected. I'm going to start with the continuum, then the SIO, and then the CS. Okay.
Okay, I'm with you.
Cool. So we detected 7 millimeter continuum emission in 9 out of the 10 regions that we observed,
Okay.
Making it, as you can see in table, what is this, 3?
Table 3, yeah.
Okay. Here we name the regions in which we detected 7 millimeter continuum emission. That's the first column. The second column is the name that we gave to each 7 millimeter core, which is C1, C2, and so on for the regions that have more than one 7 millimeter core. And these were named increasing from 1 to whatever, from east to west.
Okay.
So in column number 3, we show the 1.3 centimeter source name with which Rosero et al. Referred to.
Okay.
And as you may see here, some of the 7 millimeter cores have 1.3 centimeter counterparts and some don't. So 90% of our J candidates have 7 millimeter counterpart, but in total, 16 radio continuum sources have 7 millimeter counterpart.
Okay.
Of these 16, in 10, the case is that the 7 millimeter emission peak is found toward the center of the 7 millimeter core. And in the other 6 cases, the centimeter emission is located towards the edge of the core. And I will discuss this later, but I do want to show an example in figure 1.
Let's take a look at figure 1. Okay.
So this is our example region, IRS 18517 plus 0437. In this one in particular, we only detected 1 core. Here I marked it as C1. And what we can see in this region is in color, the 1.3 centimeter emission from Rosero et al. And we can see that it peaks in, and the 7 millimeter continuum is shown in contour. And we can see that they are coincident, their peaks seem to be quite coincident. In this case, also we have some red diamonds and a cross there that show methanol emission at 44 and 25 gigahertz from the literature. Okay. And we talk about this in more detail and for all the sources in the appendix again. But I do want to stay close to the continuum. Well, so this is an example of what we usually see. As I said, in 10 of the regions, and 9 for in the cases of the J candidates, we can see that the centimeter continuum is located towards the center of the 7 millimeter core.
Right.
Okay. So we carried out 2D Gaussian fits using CASA with the top skin fit for all the 7 millimeter cores. And we show in table 3, in columns 4, 5, and 6, some results of this Gaussian fit.
Okay.
So the type is basically their results, and results are extended in our observations. We list also the deconvolved size and the flux density obtained from the Gaussian fit.
Okay.
Now notice that there are 2 of these sources that have an E in type. They are extended sources.
Yes.
These are also extended at 1.3 and 6 centimeters. So these are probably more evolved objects that just happen to be in the region that we're interested in.
Okay.
So have that in mind, but I will not talk about them. I will not go into further details about them because we care about the J candidates in this paper. Okay. But we do want to put our results out there for in case anybody finds them useful.
Absolutely.
All right. So to further study our J candidates and the nature of the radio continuum emission, we plotted, as we show in figure 2, the spectral energy distribution of all the 7mm cores that also have non-extended radio continuum counterparts.
Okay.
And this is again our example source.
Okay.
And for most sources, just as this one, the flux density rises significantly at 7mm, which indicates that thermal emission from that begins to dominate at this wavelength.
Mhm.
So this is the case for most, but there are 4 sources where the 7mm flux is indeed consistent within errors to one of the 2 models that I'm showing here. So the dashed gray line, that is the power law fit, that explains that would be the extrapolation of the optically thick, partially optically thick jet. And the blue line shows the spherical ionized region model.
Ah,
So
okay.
the green point up here, that is the 7mm flux. And as you can see, is way above both models.
Indeed.
So as I was saying, for 4 sources, the 7mm flux is coincident within errors with either the power law fit, this gray dashed line, or the blue line.
Okay.
This could be indicating that there is no dust emission detected in this region and that it's mostly ionized emission.
Okay.
So have that in mind. I will bring that up again later.
Good. Good. Okay.
So to continue studying the continuum emission, we calculated the mass of each core using equation 1 at the bottom of page 4. For this, we made a bunch of assumptions. One of them is that the dust emission is optically thin. We also used the same dust temperature for all the sources.
Okay. Mm-hmm. Mm-hmm.
We were able to extrapolate the dust capacity from the Offenkoff and Henning 1994 work using an intermediate value for the dust emissivity.
Okay.
And for this R_G, that is the gas to dust ratio. And we calculated that for each source using equation 2 in Janetti et al. 2017.
Okay.
And we did this because, as I mentioned earlier, we are covering a large range in distances. We cover from less than 2 kiloparsecs to more than 12 kiloparsecs. So in order to account for the different gas to dust ratios in different parts of the galaxies, we decided to estimate it for each source.
Good.
Now,
Okay. Mm-hmm.
for those sources with radio continuum counterpart and that had dust emission, that is that the 7mm flux was above both of the radio continuum of both the ionized gas models.
Okay. Yes.
What we did was, if you go back to figure 2, sorry.
Yes. Yes. Exactly.
So we extrapolated here the gray dashed line, the power law fit, to 7mm, and we subtracted that to the total 7mm flux.
Okay.
In order to account for possible ionized gas emission at 7mm. So in table number 4, we show our results. We have the name of each core.
Very cool. Okay.
Yeah, then the geometric mean, that is from, we obtained this from the Gaussian fit, and the mass obtained by the method that I just mentioned. And we also were able to estimate the number density and the column density in each of these cores. So something to notice in this table is that the masses are mostly high, hundreds of solar masses.
Yeah.
And the densities are also quite high, of 10 to the 7 per meter square, meter cubed, sorry. So have in mind those numbers. I will bring it up again later. Okay, so those are basically our results from the continuum, the 7mm continuum. And I'm going to move now to the SiO10 emission. So we detected SiO in 6 of the 10 regions that we observed. Okay, so 60% of the sample of the target regions have SiO emission. In figure 3, I show again our sample source.
Okay. Oh, good. Go back to this one. Okay, good. I'm
Yeah.
with you. Yep. Yep.
So this is an example of, it's pretty similar to what we see in the other regions. Once again, as in figure 1, the contours is the 7mm emission. So this is the 7mm core,
Right.
U1. And the cross here, the white cross in the middle, marks the position of the ionized jet candidate.
Cool.
Now in colors and black contours, we show the SiO10 emission in the region.
Yes.
And I also drew a green line on top of the SiO emission to help the reader kind of distinguish a possible direction of the emission.
Right.
So again, this is an example, but we see some similar characteristics in the morphology of the SiO in all the regions where we detected it. So
Nice.
in all cases, we can see that the SiO appears to originate close to the jet candidate.
Yes.
It appears to be some elongated emission, and it's highly asymmetric or monopolar, as in this case.
Yes.
In some cases, it's a more continuous emission, and in some, there's only just knots, but generally, we see a very clumpy SiO emission.
Okay. Okay.
Also in figure 4, we show an example, again, from this region of the SiO spectrum.
Okay.
So that is the blue line here, and it's multiplied by 5 to be able to see it.
Good. Good.
And as you can see, it's highly asymmetric as well in the spectrum. It has like a wing kind of thing, and nothing on the other side, or very little on the other side.
Right. Very nice.
So that is kind of the asymmetries that we see morphologically are also observed in the spectrum. And here, the dashed gray line in the middle of the plot, that is the systemic velocity that we adopted from the literature.
What kind of velocity? Say that again.
It's the systemic velocity.
Got it. Okay, I'm with you. I'm good.
Cool. All right. In table 5, we list the properties of all the SiO jets that we observed.
Okay.
All the SiO flows.
Yes.
So here are the regions where we detected it. 18,517, the second one, that is our example source. But here are all the listed ones where we detected SiO emission. And the other columns show the peak flux density, the line RMS noise, the velocity offset of the SiO peak with respect to the systemic velocity,
Right. Okay.
the line width,
Okay.
then you have the integrated flux and the SiO luminosity, which we calculated using equation 2, again, based on the integrated flux.
Okay.
I do want to mention here 2 things. One is that the line width, we calculated it by using the full width at 0 power instead of the full width half max of the line in each spectrum. And that is because of the high asymmetries that we observe.
Okay.
So they didn't seem very much like Gaussian, so we decided to measure 0 to 0.
Okay, fair enough.
And then the other thing is that the SiO luminosities that we measured have ranged between 10 to the minus 8 and 10 to the minus 6 solar luminosity. All right.
Very cool.
So that's a summary of our results in the SiO emission. Now we can move to the CS emission.
Okay.
And CS10 emission was detected in 90% of the regions that we observed, the same 9 regions where we detected continuum.
Okay.
And in figure 5, I show an example. It's again our example source, and this is the integrated intensity emission of the CS10 in color and black contour.
Okay.
And once again, the white contour, that is the 7mm core, the 7mm emission. And I kept the green line that I showed in the previous image in figure number 3, that showed where the SiO emission, the possible direction of the jet. And we kept that to show more or less where the SiO is and how extended it is in comparison to the CS.
Yes.
And again, we show similar pictures of all the regions in the appendix, which you should take a look at afterwards, after you finalize watching this video because we see very different structures in the CF morphologically in all the cases that we observe. Yeah, in some cases, we can see that the CF emission peaks close to the 7mm core, as is in the case of our example source.
Right.
But in some cases, we can see a more extended emission. We cannot associate it clearly to a core, or it's more clumpy. So there are a lot of differences there.
Okay. Okay. Yeah.
Now, if you go back to figure 4, the other line in the beautiful spectrum, the red line that I purposely omitted previously,
Right.
that is the CF spectrum also in this region.
Hang on.
Yeah, there it is. So here what we can see is a single peak, kind of symmetric line, and emission in only a few channels. And this is very similar to what we observe in all of the regions in their spectra, but their morphological characteristics are very different. So I do want to mention that it is very probable that due to our lack of sufficiently small spacings, we did not recover all of the CS emission given its more extended nature.
Okay.
So this is all I'm going to say about the CS for the remainder of the paper. But again, if you're interested in what each of these look like, go to the appendix.
Check out that appendix.
Okay. And now we're getting to the fun part, the discussion.
Okay. I like fun parts.
Yes.
All right.
All right. So for the discussion, I'm going to have a very similar structure. I'm going to first go with the continuum, and then to the SIO, and then some other relations between them.
Okay.
So as I mentioned before, we detected 7mm cores in 90% of the regions that we observed.
Yes.
And 9 of the JET candidates have a 7mm counterpart.
Okay.
The typical sizes of the 7mm cores that we observed is about 10,000 AU.
Okay.
And as I mentioned before, in most cases, the radio continuum is located towards the center of this core. And this confirms that these are deeply embedded Young-stellar objects. They're surrounded by this big core of dust. Additionally, the masses that we estimated and the densities are quite high. So this confirms that the objects that we observed are high mass objects. And as a final conclusion of what we can see and understand from the continuum emission is that we are seeing a very similar scenario to what is predicted by the core accretion model, where we can see an accreting emerging protostar in the center of the dust core that is propelling an ionized jet.
Right.
So that is cool. That is amazing.
Very nice. Very nice.
Now, before I jump to the SIO, I wanted to talk a little bit about those regions, those 6 cores where there was an offset between the radio continuum and the 7mm core.
Yeah.
So we know that in most, not most, all of these cases, the 7mm continuum detections are weak. We have peaks of less than 5 sigma, and the offsets are also within the 7mm beam size. So we don't want to overinterpret this offset because it could just be certain errors due to our low signal to noise ratio.
Right. Okay.
But if indeed the offsets are real,
right,
one possible explanation would be that, for example, the radio continuum emission is tracing a jet knot, a jet cloud collision, and instead of being the jet more close to the protostellar object.
Yeah.
We couldn't study more deeply this interpretation in our case because only one of the cores with this offset is associated with SIO emission.
Okay.
So we couldn't connect it with another shock tracer to try and study if this was a knot or what. But so we need more data, more sensitive data to study that.
Cool. Okay.
Okay,
We'll talk
now
about-
we can jump then to the SIO emission.
Okay.
Yes. So shocks are thought to be the main source of gaseous SIO, but these shocks can be caused by cloud-cloud collisions or by jet-cloud collisions. So we investigated how probable each of these are.
Okay.
In the case of a cloud-cloud collision, we expect, based on other works in the literature, we expect the SIO flows resulting from this cloud-cloud collisions to be large scale, like several parsecs,
Right.
and with relatively small line widths in the spectrum.
Okay.
And this is nothing like what we see in our observations. We have fairly wide lines of 10 kilometers per second or more.
Okay.
And the sizes of the SIO emission that we recovered are less than a parsec.
Right.
So we discard this scenario. Now, regarding the jet cloud collision scenario, we observe that most of the SIO structures are clumpy and collimated and highly asymmetric, which are common traits of molecular jet.
Right. Okay.
Additionally, some of the jet candidates have also observations of other molecular jet, molecular flow probes like CO and HCO+.
Okay.
Now, these are
Cool.
from single dish data, but in the cases where there is an image of an outflow, when we compare it with the SIO emission that we detected, we can see that the SIO emission, the direction of the emission of the SIO is coincident with the apparent outflow axis. So it is
Okay.
our interpretation that indeed we are seeing molecular jets, and these SIO jets are being driven by a jet.
I'm good. Yep.
Cool. And well, that was like the big thing about our work.
Good.
So we connected the SIO molecular jets to 60% of our observed regions. So we can say that 60% of the jet candidates that we observed, which was a subsample, are ionized jets indeed instead of H2 regions.
Okay. Good clarification. Very good.
And we can now dig a little bit deeper on the implications of our results.
Okay.
So as a little comment on the detection rate, the SIO is usually detected, the detection rates of SIO is greater than 50% when you are observing samples with early stage high mass star formation.
Okay.
And then that number decreases as you go to more evolved samples.
Okay.
And this is consistent with what we observe. We have 60% detection rate, and in a sample that is mostly hot molecular cores or earlier. Now, regarding the other 40% of regions where we did not detect SIO, there's basically two options. Either there is no SIO there, it's lacking. These are actually not jets, maybe.
Right. Yeah.
Or the sensitivity of our observations is not enough to detect the SIO emission.
Okay.
And this would imply that the SIO line intensity in these regions is weaker than 15 milligram peak, which is our 3 sigma limit.
Got an upper bound.
Yeah. So most of our surveys use higher K transitions of the SIO, like the 2 to 1, the 5 to 4, using other instruments like ALMA or the SMA. But our detection rate is very similar to what they obtained with the brighter lines. And we also obtained this with only less than 15 minutes of on-source time. So these are not very deep observations,
Okay.
which means that these results are very promising for molecular jet surveys using this line and with the VLA, which is actually quite challenging because it's high frequency for the VLA, for the high conditions that we need to observe at this frequency.
Okay.
Now, we also studied the energetic and spatial correlations of our SIO detection.
Okay. That's good.
So in other surveys, we find that the SIO luminosity is positively correlated with both the volumetric luminosity and the radial luminosity, as we show in figure 6. Now, yeah. So the top one is with the volumetric luminosity. Versus
Yes.
okay. So you have SIO luminosity versus volumetric luminosity, and then the other one is SIO luminosity versus radio luminosity. So we only have SIO detections in 6 regions, so there's large scatter in this plot, but there is a clear correlation, and this indicates the same. From the top one, we can say that more luminous objects drive stronger SIO jets.
Yes.
And we can also say that there is a connection between the outflowing ionized gas traced by the radio luminosity and the molecular gas traced by the SIO luminosity here. We do not see a correlation between the SIO luminosity and the volumetric luminosity dust mass ratio, which is often used to indicate the evolutionary stage of the YSO. However, our sources are all expected to be in a very similar evolutionary stage. So again, maybe it is that we didn't see a correlation because we didn't have significant observations at different stages of formation. So let's not read too much into that, but we did not see it.
Not yet.
Okay, and now the molecular jet, molecular outflows correlation. Spatially, as I mentioned before, we can see that the SIO, the emission, is more or less consistent with the direction of an outflow axis wherever we have observations of another molecular tracer. However, we are saying this and comparing with data from the literature, and these are very inhomogeneous from both using different molecular tracers and very different resolutions, different telescopes.
Okay.
Yeah. So we basically cannot really make a comparison and try to connect the low scale molecular and ionized jets to the larger scale molecular flows until we have a more homogeneous sample.
Okay.
We also searched in the literature to try and connect the SIO emission with other shock gas tracers.
Okay, sure.
So we searched for 2.122 microns H2 emission, and we found that in 2 of the regions where we have SIO jets, there are H2 features, but only one of those, that feature seems to be coincident with an SIO not.
Okay.
And we also searched in the Spitzer archival data for 4.5 micron extended excess emission, as we can see in figure 7 here.
Okay, so
this is an example of an IRAC. Yes, this is the color composite. And again, this is our sample source. And here we have 3.6 microns in blue. Red is 8 microns. And green is the 4.5 microns, which is the one that traces shock gas. So the other elements in this image are the 7mm contours, which this time are blue. The cross in the middle of the 7mm, that is where the jet candidate is, or the jet, because we already established that these are jets.
Right.
Yeah. And the magenta lines, the magenta contours show the SIO emission.
Right. Okay.
So we detected excess 4.5 micron emission in 2 regions. And in both, what we see is something similar to this, that the 4.5 micron green emission here is quasi-perpendicular to the SIO emission.
Okay.
Okay.
All right.
So we were expecting it to be like more correlated.
Yeah.
But we observed this in both of them. And again, there's only 2 sources, so there's not a lot that we can say statistically about what this means.
Yeah. Pretty bright there. Yeah. Okay. Good.
Okay, so those are all of our results.
Cool.
I'm gonna go quickly through the summary of our discussion. Okay. So we detected 7mm continuum in 90% of the JET candidates. And in all of them, we can see that the JET candidate is located towards the center of the 7mm core, except for one. We also find that the JET candidate is usually in this very massive and very dense core, which is expected from a very deeply embedded young stellar object.
Okay.
We also were able to connect the molecular SIO jet of 60% of the sample to the JET candidate.
Yes.
Confirming the jet nature of 60% of our sample.
Yes.
And although our sample has a large scatter, we find a positive correlation between our measured SIO luminosities and the bolometric luminosities of the object and the radial luminosities from the JET candidate.
Yes, that was figure 6.
Yeah. So our results demonstrate that both this line, the SIO10 line, which is expected to be not super bright, and the VLA are both suitable to carry out molecular jet surveys. And it adds to the growing list of studies with high detection rates of SIO emission in the earliest stages of both low and high mass star formation. So this is a promising path for the future, for future studies. And before I leave, I do want to thank again all of my collaborators. We're amazing. I also want to thank the National Science Foundation for supporting my research, and the NRAO for their publication support as well.
Cool. Very cool. Very, very nice. Tatiana, thank you so much for walking us through your very lovely PJ supplement article.
Of course. Thank you so much for having me. And this was a very fun project. It was something quite new.
Yeah. So you touched on it a couple of times as you walk through your article. So let me push on it a little bit. You know, where do you think we go over the next, let's say 2 to 5 years, or a graduate student career, as the case may be, on this topic? So you've basically established sort of the validity of this tracer. So is there, do we triple, double, triple, quadruple the size of the sample? Are there other telescopes that might be useful to study these? Is there theoretical models that could be done? Laboratory astrophysics on maybe some of those opacities, those molecular opacities from where you get the masses. So just sort of next steps on where do we go over the next couple of years?
Yes. So I mentioned in the beginning that there were basically 2 ways to distinguish if they were jets or H2 regions. One was studying the molecular emission, and the other one was studying the continuum with higher resolution. So we did that as well. I'm working now on the imaging of higher resolution VLA data, where we're trying to see if these jets are resolved, if these are jets, if they're not.
What are they?
So that will help us both cement the results in the Rosero survey, but also if most of these are still unresolved, that would mean very, very dense and very highly compact objects, which could be something that some new stage or undiscovered stage limits in the H2 region world. So that work, as I said, I'm working on the imaging of that. I am hopefully at the end of this year, I will have a draft. So soon you might see me again.
Very good.
Yes, and we're also working on a survey of, as I mentioned, a more homogeneous survey of molecular emission. We're gonna try and we're gonna propose for ALMA observations of molecular tracers like CO or HCO plus, maybe higher energy CO rather than 2-to-1, to try and connect the small scale jet and the large scale flows. And that way try to study the momentum transfer between the two and how mass accretion and mass loss processes are related.
Cool.
Those are more or less the last few projects of my PhD. Yeah.
Nice. Very nice. Well, I certainly look forward to seeing this field move ahead over the next couple of years.
Yes, me too.
I look forward eventually soon enough to be calling you Dr. Rodriguez. So very nice.
Yes. Thank you very much, Frank.
Yeah. So very good. Thank you so much once again. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.